Okay, so now let's look at an example from the book. It's 6.4.4 where we have a harmonic oscillator or an undamped system with a forcing function that ends at time equals 1. So we apply an increasing amount of force until time equals 1, and then we apply no force. We want to see what happens. Now, what's really interesting about this is that we can use this almost like an impulse to give a system which should have no motion. X of 0 is 0 and x prime is initial velocity is 0, initial position is 0. So it should not move at all, but then we give it an impulse or a short time frame function. And then it should start moving. Now, a way to think about this is, say we're starting with someone on a swing set who doesn't know how to swing themselves. Initial position and velocity is 0, they're just sitting there. And then you give them an impulse and then let go. So let's see what happens. First off, we should define our piecewise function in terms of unit steps. So we have a function t that is on, and then we turn it off at time equals 1. So this is the function that is being turned off, and that activation happens at t minus 1. So we get s squared plus 4 times our capital X is equal to the transform of t 1 over s squared minus the transform of t times u of t minus 1. Well, to make this shift work out correctly, we want to think of this as t minus a t minus 1 u of t minus 1. And then because we're subtracting with a negative, we're adding in this extra unit step. We need to then subtract off 1 u of t minus 1, like that. So now we have the form that's shifted correctly. Or I'll just write this as a transform of f plus s x0 plus x prime of 0, which are both 0, so keep that in mind. Here we have the transform of t minus the transform of t minus 1 times u of t minus 1 minus the transform of u of t minus 1. So 1 over s squared is the transform of t. Then we have an activation, so we pull out e to the negative c times s. Again, here c is 1, so that's negative s times the transform of t, the unshifted version of it, minus transformation of the unit step just by 1. So that is simply an e to the negative s times 1 over s, like that. And finally, we can combine this together to give us a 1 over s squared minus e to the negative s times 1 over s squared minus e to the negative s times 1 over s. So let's combine that all into two pieces, one that has an activation, one that doesn't. So we have a 1 over s squared times s squared plus 4. That's the piece that is starting out before the activation, or deactivation if you want to think of it that way. And then we have minus e to the negative s times a 1 over s squared plus an s over s squared, and then we multiply by s squared plus 4. Okay, now notice that these denominators will be the same. So our partial fraction decomposition, even though it has two different pieces here, will end up with the same expansion to just an s squared and s squared plus 4. Be very careful not to combine these two in the partial fraction decomposition, because we cannot treat this e to the negative s as a constant. So there's two pieces that need to be expanded. So since we're doing very similar partial fraction decompositions, I will do one at a time and use the same letters A, B, and C, and D. Okay. Now, we only have one singular value to work with, so it might be simpler just to break up this in terms of the powers. The highest power here is a cube. So we have a s cubed plus c. Then the s squared terms. And here, that's an s b plus d s squared plus the s terms for a. That's it. And then the constant term for b. I'm sorry, s times s. Okay, and all of that equal to 1. So let's start off with the ones. 1 is equal to 4b. Okay, b is 1/4. The s terms. 0 is equal to 4a. A is 0. S squared terms. 0 is equal to b plus d. So d equals negative b is negative 1/4. And s cubed terms, 0 is equal to a plus c, which means c equals negative a, which is 0. And there is our first expansion down. Then we subtract e to the negative s times, and we do this expansion all over again. So we need to solve for an a, a b, a c, and a d. And the only difference is that it now equals 1 plus s. So we go down the line. Same conditions on the right, but different conditions on the left. We have a 1 for 1, a 1 for s, 0 for s squared, 0 for s cubed. So solving for b, b is 1/4. Solving for a is 1/4. Solving for d, negative b, so that's negative 1/4. Solving for c, negative a equals negative 1/4. Okay, so now we have a little bit more to work with. So that gives us a 1/4 of 1 over s plus a 1/4 of 1 over s squared minus 1/4 of s over s squared plus 4 minus 1/4 of 1 over s squared plus 4. And these plus 4 I need to think of as a 2 squared. Okay, so now let's transform back. No, before we do, let me remind you how nice it was that we had the same denominator. Even though we had different numerators, we had to do the partial fractions twice. We basically used the same work, right? The expansions on the right were the same because we had the same form. Same denominator means the same form of the expansion. The only thing that's changing is how much of each piece we have on the left. So when we're using the basis expansion form, it's really quite nice. If you plugged in points, it would be the same idea. You'd have the same point values on the right, but different point values on the left. So, that's clever. Okay, so now we wrap it up by inverting our transform piece. Before we do so, I want to go through the pieces I have left and see if I recognize all of these pieces in my table. So 1 over s squared, I recognize that as coming from t. 1 over s squared plus 2 squared, that's really close to a sine, except I need a 2 in there. Now, I recognize the transform of the sine of 2t. And e to the negative s tells me there's an activation or a unit step happening at c equals 1, or time equals 1. There's a constant 1. Here's a t. Here is a cosine of 2t. Here, it's close. It's almost a sine of 2t. We just need to factor another 1/2 out. Okay, so now we're ready. So first, let's have that factor of 1/4 out. I have a t minus 1/2 of sine of 2t. And then I subtract this activation unit step times some other transform pieces. So I look back at my second property and I work backwards. I have an exponential at c equals, with the c equals 1 value, times transformation of several different functions, or a combination piece. I want to turn it into a unit step function times each of these functions shifted where they once were a t to a t minus c, in this case 1. So first I factor out the unit step, and it doesn't matter what order you write this. I look at my function. This is a 1, so that means I have a 1 shifted, replacing all t's with t minus 1. And then I have 1 over s squared, which is t, so that's a t minus 1. Then I have a minus cosine of 2t, so that's a cosine of 2t minus 1. And then a minus 1/2 of sine of 2t, and I replace the t again, so sine of 2t, 2 times t minus 1, like that. Whew. So there's an example of how we can use these switch functions to expand it outwards. If we wanted to, we could use the angle sum formula to expand those cosines and sines out, but really I think it's just fine, because what it's telling us is that at time equals, oh, not c, sorry, wow, so close. At time equals 1, we're going to activate what looks like a cosine of 2t, just shifted over by 1. And then here, this will look like a sine of 2t, just shifted over by 1 as well.